Hi, everyone. Can everyone hear me in the back? Okay. Hi, my name is Kelsey McDonald. I am going into my fourth year as a PhD student in the Psychology and Neuroscience department in Scott Hutel and John Pearson's labs here at Duke. And for my dissertation work, I've been using computational modeling and machine learning to study human strategic decision making. And the way we study human strategic decision making in my lab is a game similar to Pong. So we have people come to the fMRI scanner at the medical center here at Duke, and we have humans play essentially Pong. It's called the penalty shot game. So they are controlling the green ball, and they're moving at a constant horizontal velocity. And they have a simple goal just to get to the white goal line before the red bar representing a goalie can stop them. On half of the trials, they're playing against another human who's sitting outside of the scanner with me. And on the other half of the trials, they're playing against a computer algorithm. So we were using this paradigm to study how people differ in their strategic decision making when they're playing against agents of different types, so humans and computers. The data that is generated by the behavior of these participants is quite rich. So this is a trajectory from just one trial from one participant. And this is just from two participants. So each graph is one subject's trajectories overlaid on top of each other. In blue is trials they played against the human, and in green is them playing against the computer opponent. And so to make sense of this from a psychological perspective, we used a Gaussian process classification approach to predict two variables of interest that were important to our science. So we wanted to predict, from a reinforcement learning perspective, we wanted to predict their policy or their future actions. So given the state of the game at time t, we wanted to predict the action that they would take at time t plus 1. So to take this trajectory as an example, we wanted to model the change points because we interpret that as a change in strategy. They were going up and then they jammed the joystick down, or vice versa. So our policy function wanted to model these change points. And we also wanted to model, based on the state of the game, what is the probability of them winning the trial given that they have a given policy pi and the state of the game s of t. And so from these flexible Gaussian process models, we're able to characterize multiple variables of interest, such as opponent sensitivity. So we can tell at an instantaneous time level to what extent are these two humans or human-computer dyads dynamically coupled. So how much does my actions, if I'm playing the game, how much does my actions depend on my opponent's actions? And we can also determine the variable in green, which is the probability of them winning, given that they make strategic decisions to make their final change point at a given time period X. So when are they going to make their final change point to say, okay, I'm just going to continue to, I'm going to continue along my trajectory, and I've made my final decision, more or less. And so these are representing the policy and value functions of each player. And if you're interested in what strategies separate good, skilled players from bad players, come talk to me at my poster over there. All right, thank you for your attention.